11.5 is going to continue talking about this idea of sums in geometric sequences. So if we go back to our example about the bouncing ball from yesterday's lesson, the question really is how much is that ball rebounding each time? And what happens is it's actually rebounding 60% of the previous bounce. So theoretically, if that happened, would it ever stop bouncing? And now we're not talking real, we're talking theoretically. We're not going to take into account gravity or friction. It would never stop bouncing because you could always take 60% of the previous number. It's going to be teeny, teeny, tiny, but you can always do the math, like I said in theory. So what does that have to do with us? With infinite geometric series, we can sometimes do a sum and sometimes not. Now, arithmetic series, that's different. This is geometric series. So we are going to be talking about infinite numbers of terms. We're not going to have that a of n anymore, a of 6, a of 20. We're going to be talking about for all of infinity, what does this series add up to, which is kind of a crazy concept. So our key question is, how do we know? How can you tell? Some do and some don't. This is your key answer right here. If your common ratio is between -1 and 1, sometimes you will see it written like that. The absolute value of r is less than 1. If you remember back to the beginning of the chapter, we learned that that would expand out like that. So when you find r, if it's between -1 and 1, there will be a sum. So let's look at these examples. Is there a sum? So here's a1, a2, all the way out. We find r by taking any term divided by its previous term. I'm maybe going to pick easy terms, so I'm going to take -12 divided by 4. So my r is -3. That is not less than 1, so there is no sum here. If I look at example B, here's a1, here's a2, a3. I don't have any nice neat numbers, so I'm going to go ahead and find r here, and I'm going to take -3/2 divided by 3, which means I'm taking -3/2 divided by 3, or multiplying by 1/3. It's reciprocal. Your 3's cancel, and r is -1/2. That does meet my criteria, so yes, there is a sum. So then what? Well, there's another formula. And the formula says to find the sum of an infinite geometric sequence, you take first term divided by 1 minus r, which is that common ratio that we are finding, how much it goes up or down by each time. So, kind of to recap, what we were doing when we were finding the sum of a6, for example, was a partial sum. We were adding up part of the series, because remember, these series are infinite. Now, if we go to a truly infinite series and it has a sum, which remember means that r is absolute value less than 1, then it's a convergent series. What happens is it's going to, over time, balance out towards a certain number, and no matter what we are then multiplying by, it, like that 60%, it really doesn't change it. So it's going to converge on a value. So, sigma notation. Now, sigma notation for series like this look a little different, and I'm going to do kind of a generic one here. So we're going to go to infinity. We're going to have n is equal to usually 1. Then we're going to have some number, and then we will have some number in parentheses to n minus 1. Now, whatever that term is outside of the parentheses is always your first term. It is your a1. Whatever is inside the parentheses is your R. So we can quickly see, given a sigma notation, what our A1, our R, and our N are going to be. So A1 is 5. R is 1/2. Is there a sum? There is a sum because R is between -1 and 1, and N is infinity. So, because there's a sum, we go to that convergent sum formula, and we say sum is equal to the first term, 5, over 1 minus R, which means I have 5 over 1/2. 5 divided by 1/2 is exactly the same thing as 5 times its reciprocal, which means that this sum will converge on 10. Now, repeating decimals as fractions. I'm going to teach you a very simple method for doing this. First step, we're going to write an equation with the decimal. And we're going to do it just like this. We're going to say D is equal to 0.25252525. Throw a few of them on there. That's fine. Then, you're going to multiply that equation by 100. So you're going to get 100D is equal to 25.252525. Here comes the cool part. Step 3 is subtract the two equations. And when you do that, always put the bigger one on top. So I have 100D, which is equal to 25.252525, minus essentially 1D, which is equal to 0.252525. Make sure you line up your decimal points when you do that. I end up with 99D, remember there's a 1 here, is equal to 25, because those guys all disappear. Solve for D, your fractional equivalent is 25 over 99. And that is a pretty useful skill to have as you need to deal with R being a repeating decimal. Potentially you can turn it into a fraction to use for the rest of your calculations. And that is all there is to lesson 11.5.